Hello, students getting into 3.3. Section 3.3 is, well, we're moving through the operations. You saw 3.2 is addition. This is subtraction. Take a look at the Common Core standards that are listed here. We got grade 2. This is second grade. They should be able to fluently add and subtract within 100. They should be able to add and subtract within 1,000. Notice it doesn't say as fluently, so it's not as quick, it's not as efficient, but they can still do it. Okay. Understand adding or subtracting 3-digit numbers. You add or subtract hundreds, tens, and tens, ones and ones, and sometimes even compose or decompose tens or hundreds. So the idea of composing and decomposing is still here. Composing when you're adding, decomposing when subtracting as needed. But we also saw in 3.2 that we could decompose numbers in order to add more efficiently. And I think that's one of the pieces that as a teacher, I really appreciate now that I've, well, now that I am where I am with the history that I have and all the experience. But I think too often as a teacher, even kind of growing up in my own schooling, I remember questions that looked like this: 13 plus 48, right? And I bought an equal sign and it was always kind of going this direction. It was very rare. I don't even remember a time where somebody said 48 equals what and put a plus sign in there. So I got so used to thinking like the equal sign was the idea that I need to do something, and the thing I do is this operation, that I just kind of spaced out. I started not even looking really at what was going on. And instead, going this way, where we decompose a number, you could make a lot of statements, right? It could be 47 plus 1, could be 46 plus 2, right? Could be 45 plus 3. But I could change the operator over here, and all of a sudden it becomes something like 50 minus 2. So if I was decomposing 48 and called it 50 minus 2, in a sense, just rewriting the number, I could really start doing these problems much quicker, right? I could do 50 plus 13 very quick because that's 63. I don't have any ones to worry about. Take 63 and then take away 2 at the end. So again, very quick ways to go forwards and backwards, and that's what we're looking for with these types of problems. All right, let's talk about subtraction models. Subtraction models are a way to undo one of the other operations. If you go to higher level math, and I'm pretty sure most of you won't, but if you did, you'd realize subtraction is not one of the key operations. As a matter of fact, most of the time subtraction is defined in terms of addition, which means addition is the operation we use. Subtraction is something we might use maybe if we're trying to be maybe a little bit more efficient, but it's not an operation that we use in what's known as a mathematical field. So we have what are called field properties, and addition and multiplication are the two field properties. Subtraction, division, really in a sense don't even exist. And if you could imagine every subtraction problem, and we'll see this when we get later in the textbook, every subtraction problem could be rewritten as an addition problem. And if that's the case, then we really don't need subtraction ever. However, if you're teaching younger kids, they're not at a level where they can really grasp that. So introducing subtraction as an operation is just fine as long as you define it very clearly. So we're going to define this as an inverse operation. And we're going to talk about the models. We're going to have a takeaway model, number line or measurement model, and a missing addend model. Okay, now we also have the comparison model, which is used quite a bit. Let's take a look as we go through some of these. Some of you may be familiar with a few of these models. The idea of the takeaway model. What do we do with takeaway? Put a certain number of objects into a space, physically take away a certain amount. So the problem 8 minus 3 equals 5, you would start with 8 blocks put in there, and then you would physically take away 3 of them. And of course, that leaves you with 5 remaining. Okay. So this is similar to what we did with sets, but with sets, we had to make sure they were disjoint. Here, now we want to start thinking about using something like set difference. And that's what we did in section 2.1, 2.2 and 2.3 when we did set difference. And set difference was really focusing though on Like if I had A set difference B, it's the objects that are in A but not in B. So if you were kind of transferring that and you say, well, how many objects are in n of A minus B? You might say, well, it's like the number of things that are in A, because I take all of that, but then I have to take some of them out. And what am I taking out? And be careful here. Be really careful. It's tempting to say it's the number of things in B. I guarantee it's tempting to say that. So I'm just going to put kind of a little smile, well, an unhappy face, a little tear dripping down, because remember, in order to be removed with the set difference, they had to exist in A. So you don't want to be thinking about this as the number of A minus the number of B and say something like this is like n of A minus B. It's not. And the reason is B, so if you had a set A here, and A was a 1, 2, 3, 4, and a 5, and set B is the set 3, 4, 5, 6, let's say, then the number in A is 5, the number in B is 4, but the number that is in A set difference B, well, the only thing that I would remove from A is where they match up, so I'd pull those 3 items out, leaving myself with 2. And 5 minus 4 does not equal 2. So remember, the only things being removed are the pieces that they share, not everything that's in B. All right, so I think that'll help you a little bit with the now try this. Moving on to the number line model. This is kind of fun. So I remember, yeah, I remember someone telling me that you could think about this like it's a car. So when we were doing 5 plus 3, or 3 plus 2 even, so 3 plus 2 on the number line, start at 0, right? And you would go 3 units forward. So think about your little car, and I'm going to draw it like it's a pickup truck. Okay. So we can see where the front is. Okay, put a little window in here. Oh, better give it tires. Okay. So here we go. We just moved 3. Addition is like keep moving in the same direction. So keep moving in the same direction. A positive number means I'm going to keep moving forward in the same direction. And that's why I end at 5. So addition is kind of keep moving in the same direction. When you encounter a subtraction sign, it's flip around in a sense. Okay, with a UE, hit the E brake and Fast and the Furious style. Okay. So when you see 5 minus 3, what you do is you start here, yes, and you move 5 units forward because that's what your truck is doing. Then flip it around, and because it's a positive 3 here, we're going to go forward 3 units. Now my vehicle's facing the other direction. So I end up sitting here at the number 2. Okay. So that's the idea that someone was telling me. And I was like, I could kind of see that. Okay. To be honest, it's almost easier. Again, it's almost easier not to have subtraction, because if you're always going with forwards and backwards, you can think of those as positive and negatives. And yes, we will see in a couple of chapters. Again, this is just the age level piece. They've kind of determined that seeing things as negative numbers may not work well, depending on where the young the child's mind is at with developing these concepts. So 5 minus 3, yes, we will get to this stage where 5 plus 3 is the same as 5 plus negative 3. And this one, when you get higher in math, or maybe you'll start to buy into it now, you'll realize this one is significantly easier to deal with. I don't need a new operation. So if I was in my truck and I go and I say, well, what is 5 plus negative 3? I go forward 5 because it's positive, keep my car facing the same direction, and then I put it in reverse. So this little negative here is like put it in reverse and just back up 3 units. Okay. Now my vehicle is sitting right here. It's the same answer, but I don't have to think about kind of do a subtraction. I have to flip my car around and drive forward. So to me, I definitely prefer adding the opposite. And we'll see how that goes the rest of the time. Okay, missing addend model. Missing addend is thinking about something known as a 4-fact family. And so when you think about a problem, let's just do something nice like 2 plus 3. 2 plus 3 is equal to 5, right? Okay, that is one fact. Now, if we use the commutative property, I get 3 plus 2 is equal to 5, and I get that one for free, but it is still a second fact. Then I could do subtraction. I could say 5 minus 2, and 5 minus 2 is 3. That's the third fact. And I could also get 5 minus 3 equals 2. That's the fourth. So we tend to call this a four-fact family. With three distinct numbers, you can kind of create these families. So when you are doing subtraction, thinking about subtraction, if I wanted to do 5 minus 3 equals some number, I could really just say, you know what, let me rewrite that as 3 plus that number. And so all I'm doing is rewriting it, in a sense, almost algebraically. But really now, you've turned it kind of into an addition problem. And a student could solve this by adding up. So this is called missing addend because we're missing one of the pieces right here that I would add to get to 8. And so that is how we could do the subtraction. You can almost see these are going to be mirrored as we do. This is addition and subtraction. We're going to mirror those when we get to multiplication and division. So just like we had a missing addend, we will soon have a missing factor, which is what we multiply to get a number. Okay. All right, this is the missing addend approach. 8 total, 3 right here. How many more? We could see it on the number line because I know 8 is where I need to end up. I started with 3. How much more do I need? And we could count them out as we're learning subtraction. Okay. All right, let's see then. And again, we don't really call it, I want to be really clear about this. We don't call it algebra. It's algebraic thinking. Okay, so the difference is with algebra, I would write this as 3 plus x equals 8 and ask you to solve it algebraically by subtracting 3 from both sides. That's algebraic. This is a very big term in mathematics education, especially at the K to 6 level, called algebraic thinking. We're thinking and we're involving unknowns, which is very much algebraic, but we can still solve the problems even if we're not sure of all the algebraic steps. All right, so here's a definition of subtraction, and I want you to understand. For any whole numbers, A and B, so we have what conditions? We're dealing with whole numbers right now. And notice we are saying specifically that A has to be greater than or equal to B. Now, that is not true in all cases. The definition of subtraction can be expanded. Right now, though, we're dealing with whole numbers. So if you had 5 minus 5, you'd get 0, and that's okay. But if you had 5 minus 6, we would get -1, and -1 is not a whole number. So that's why our definition stipulates that we have to have A greater than or equal to B. We need to end at 0 so that we maintain the number structure that we have to this point in time. This is also why some teachers might have said to you, perhaps, yeah, you cannot subtract a bigger number from a smaller number. Completely wrong, but it basically you can, it's just not a whole number anymore. All right, now, because subtraction is not commutative, right? Think about it. 3 minus 2 is not the same thing as 2 minus 3. So I can't flip those around. We need different terms for each one. The first number that you see is called the minuend. The second one is the subtrahend. Subtrahend is the number you subtract. Okay, so we need a different term. Which one is the minuend? Which is the subtrahend? I did not choose these terms. They've been around for a long time, but those are the terms that we have. You'll also notice in this definition, A minus B is the unique whole number. Okay, and it's a unique whole number C such that B plus C equals A. So B plus some number has to get me back here. That number has to be unique. It also has to exist, right? What we're saying is that when we do this, there is a whole number that works, that's existing, and there is exactly one. That's the uniqueness, right? So again, these are important definitions, especially if you continue on in mathematics. We want to lay the foundation for understanding the definitions. And you'll take a look here. It says da 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 da. An alternative but equally effective definition for subtraction begin by stipulating, without stipulating this, for any whole numbers a and b, a minus b is the unique whole number c if it exists, such that b plus c equals a. Okay. So we can refer to this page to see how students use the missing add-in model, but it's the unique whole number if it exists. And if it's not a whole number, then we would say it does not exist. Okay, that's fine. But if it does exist, then it has to be unique. So if there's an answer, there's only one answer. We do not want something like this. This would be a crazy world, right? Where we said, okay, 13 minus 5, and some student gets 8, and another student gets 7, and we say, oh, they're both correct. So that's why we need a unique answer here. And it reminds me of my dad's joke. So you're going to have to tolerate some of these because my dad was a teacher for 37 years. He would say, how do you catch a unique rabbit? And I was like, I don't know, Dad. How do I catch a unique rabbit? He'd like, unique up on him. Unique up on you, sneak up on him. I was like, okay, that's pretty funny. He goes, well, how do you catch a tame rabbit? I was like, I don't know. He goes, tame way. So there's your dad joke for the day. Enjoy that one. All right, let's see here. There's the 4-fact family we were talking about. Notice they've put it together in a triangle. But again, the shape is really irrelevant. You got to be able to see that 5 plus 7 gets you to 12. 7 plus 5 gets you to 12. 12 is the higher number. So 12 minus 7, like subtracting, kind of comes down the sides and would get you to the other. Right? All right, let's jump on. Crack on. Here we go. This is grade 2. They're doing subtraction up here. Comparison model. Now, this one is kind of a big one. So it's how many blocks do you have? How many blocks do I have? And I compare yours to mine, almost creating that one-to-one correspondence that we saw back in section 2.2. So with that, 3 of these shapes had a one-to-one correspondence. The difference is how many shapes are remaining. So I am actually comparing them to mine, yours to mine. I'm comparing them. I'm not taking yours away. I'm not taking any of those pieces away. I simply compare them, and it's another approach or another model. Okay. All right. So if you've been paying attention, you probably heard a few of these things. Is there a commutative property, associative property, and identity for subtraction? This is a now try this. And it's up to you to figure out whether those are true. Up here, it does talk about closure. I'm not going to read that for you because it's only a couple sentences. I want you to understand, are the whole numbers closed under subtraction? Okay. Using whole number addition and subtraction in equations. So now think about these. These are the same type of things, but now we're using it as more algebra. Okay. You're a college student, so you had intermediate algebra to get here. The expectation is you could solve these problems and write the solution for each of them. Okay, notice some of them have addition, some have subtraction, some of them have an and statement. And an and statement means what? All of them have to be true. That's correct. In this case, there's only 2. You could say both have to be true. All right, subtraction algorithms. Now we're getting into how to do it, right? Here's the idea. We saw all these great ideas and how to model it. Now we start talking about what are the steps we take to do subtraction. Okay. So one of the big pieces that they're pushing more in school now is thinking of all the different ways you could think of numbers. And we saw that with place value, and I'm going to just pause for a second because I think it's really important. So if we had 243 as a number, right? And you can think of that in column form, right? So here's your ones, here's your tens, here's your hundreds. You could think of that as 2 groups of 100, 4 tens, and 3 ones. Totally agree. You could think of it as one group of 10 with 14 ones, one group of 100 with 14 tens and 3 ones. Why? Because 10 tens is the same as 100, so we can regroup and fair trade those anytime we want. We could also say 0 groups of 100, 24 groups of 10, and 3 ones. Yes. If you think of this with money, you'd have no problem saying the person has the same amount of money if they had 24 $10 bills and 3 ones as a person who had 2 hundreds, 4 tens, and 3 ones. It's the same. Now, of course, we can't write all of these this way. We could, like, especially this one, we couldn't write 1, 1, 4, 3 because it looks too much like 1,143. But we could also continue on. So this could be 0, 23, 13 ones. That's perfectly fine. Oops. Timer just went off. I gotta hit pause for a second because I am baking some bread. Give me one quick second. All right. I know it doesn't look like I did anything from your view, but the top wasn't quite done, so I gotta get a little bit crispier crust on it. I got like 4 minutes. All right, so let's see here. So these are different ways to rewrite them. When a student sees they can rewrite them as this, it doesn't become such a problem for them to write something like this, what you would typically say is borrowing, but we now know is just completely fair trading or regrouping, or maybe decomposing as well. I would use that term. Okay. So if I was doing a problem like 243 minus 61, I would regroup. Then I'd have enough of these 10s to be able to remove some of them, but I already had enough ones, and you can see I cross off the number of ones right here. So 3 minus 1 is 2 ones that are remaining. I fair trade, then I pull out a group of them, and it says take away 6 of them. So it doesn't really show the taking away of the 6. I wish it did. I would actually, if I was doing this and I asked you to do it, I would say take 4 of these, 5, 6. Take those out of here, right? Show me that you're removing them. Just like this, show me that you're taking them away. And then you'd be good to go from there. Okay. Let's see here. What else do we have? We have subtraction using all the properties. These are all the properties you would be doing. Here's equal additions. I call this equal addends because that's all we're doing. And if you're doing this with subtraction, you're welcome to do this again. As long as you add the same thing to both numbers, you're really not changing the subtraction because the distance between two numbers, again, they didn't quote subtraction to you that way, but that's really the concept. It's the distance from one number to another number. And so if you move each number up by 7, it becomes a lot easier to do the subtraction. Again, here, if I move each number up by 30, again, now it's way easier to do the subtraction. And I don't have to worry about doing any regroupings. Okay, any regroupings that would involve crossing numbers out. So totally fine to do this one. As a matter of fact, it's one of my favorites is this equal additions, especially if it's quick to do it. Now, to be perfectly honest, I probably wouldn't have used exactly the way that the book approached it. Not that it's wrong. There's nothing wrong with it, but the 5 minus 3, I can already get a 2 out of this, so I don't have to do anything there. What I might add is just a 40 to each one of these. So now I have 295 minus 203, and now I don't have any of the regroupings, and I can see 0, 9, and 2, and I get that answer without having to do 2 regroupings. So you're in charge though. If you want to do 2 regroupings, you want to do 5 regroupings, totally and completely fine. Nothing wrong with that. School book page for the equal additions, such a fantastic one to do, especially when numbers are really close to 10s. Like this problem here for kids, this problem would have been really cumbersome before, but if you say, hey, wait a minute, why don't I add 1 to each of these? Now I have the problem 74 minus 10, and I got to tell you, it's so much quicker. Like it's so much quicker, right? So keep that in mind as you do it. All right. And what was this one? Yeah, second grade once again. All right, this one is the counting up algorithm, sometimes called making change. If you go to stores, occasionally you'll have someone who is maybe a little bit older and they count the change back to you. Instead of just saying, here's $2.42, they'll count up. So if you owed $11 for your groceries and you paid with a $50 bill, the cashier starts by saying 11. Okay. Oop. Oh, the bread's almost done. They say 11 because they're giving you your groceries, $11 worth of groceries I'm giving you. Then I count back with $1 bills and I say 12, 13, 14, 15. So I just gave you back 4 $1 bills. Then I put a 5 on top of that and I call it 20 because 15 plus 5 is 20. So I'm counting up. Then I add a 10 to that, which gets me to 30, and I add a 20 on top of that to get me to 50. So the change that came back is the difference. Now the difference is all of the money, which is $39, but I'm actually counting those up as I do it. Okay. Let's see here. Oh, shoot. Timer's going off. Give me 1 second. Let me grab that bread. We'll see how it looks. Okay. So I keep running away and hitting pause, and I know it doesn't count for time for you, but so there it is. I don't know. I've never really, it's like my third time making it. So I forgot to score the top too. So it kind of split. But anyway, I'll hopefully see you're all trying something new. I'm trying something new too. All right, let me set this down. It's very, very hot. Okay. All right. So bread is done. I don't know if it's done or not. I mean, it's done cooking. It's out of the oven. Let's get back to this. All right. So the idea here is one of the last ones we talked about is called the trades first algorithm. Now, trades first with 37 taking away from 122 is, let me show it to you here without manipulatives from the book, is to actually take away all the trades that you may need as we go. So let's start with the 122. You know you got to take away 7 units. So trade one of your 10s for 10 additional ones. Don't take anything away yet, though. Then you can say, okay, now I need to take away 3 longs or 3 rods, but I only have 1. So swap your 100 for this. So if you take a look here, you're taking one of these, swapping it out here, take one of these, swapping it down here. You're doing all the trading first. Once you have everything traded, then you go through and do the actual subtraction. Now the subtraction here would be, let's see here, I need to take away 85. So I take away 5 of these. 1, 2, 3, 4, 5 right there. There's 5 of those. I need to take away 8 of these. So let's see here. 1, 2. Wait, no, I'm not taking that away. How many do I have to take away? I need to take away 3 longs. So I need to take away 3 longs. So I take away 3 longs right here. And I just kind of take those completely out of the picture. That leaves behind 8 longs or rods and 5 of the unit blocks or ones. Okay, so you can kind of see it here. This is the picture that's happening. The symbol above is with the actual base blocks. These are not with base blocks. These are written down a little bit differently. Let's see here. Understanding subtraction in bases other than 10. Hey, it's the same thing. Subtraction doesn't change, so you're in good shape. Yeah, so if we go forward here, looks like they're probably going to do one. If you wanted to use the base blocks, like actual blocks, they have them in either plastic or wood, or you can make your own out of paper. So if you had 3, 2, base 5, you got to remember it's not 32, right? It's 3 groups of 5 and 2 ones. So really, I want to take away 1, 4, which is 1 group of 5 and 4 ones. I don't have enough ones. So swap one of these for 5 individual pieces. Okay. And that gives you this picture right next to it with 2 longs and 1, 2, 3, 4, 5, 6, 7 individual pieces. Then take away your 1, 4 right here and actually pull those out and away. You find you're left with 1 of these, 3 of these. So I have 1, 3, base 5. Now you can regroup that. You can absolutely regroup that. And I think sometimes students get a little bit stuck on this, but if you did it vertically, so it's more traditional, take away 1, 4. Both of these are in base 5. Both of these are in base 5. I would come here, leave 2 remaining, bring one of them over here. And now this is the tough part. Again, I think some of you are going to struggle a little bit, but just try to fight through it because it's base 5. So if you say 12 to yourself, remind it's not 12. It's 1, 2, which is a group of 5 and 2 ones. 1, 2 is 7. So this is 7 minus 4, which gives me 3. 2 minus 1, which gives me 1. And there's my final answer. Okay. Again, I think it's much easier. And I think what I'll probably do is do an activity where we do use chips, probably poker chips, because the base blocks, they are kind of cumbersome. And they're also way expensive, typically. So finding different base blocks. Right now, these days in educational materials, you have a hard time finding anything other than base 10. And base 10, because it's so long and so big, it becomes cumbersome. So we'll definitely kind of show some base 10 blocks as we go. All right, mental computation. So if you're doing mental computation, you could do the same type of thing with breaking up and bridging. Breaking up means taking just the 10s away. So 67 minus 30 gives you 37. Then deal with taking away the 6. So breaking it up means instead of dealing with like thinking of doing a 2-digit number minus a 2-digit number. It's really a 2-digit number minus 1 digit. Then when I'm done with that, minus one more digit. Okay. Trading off, fantastic. Okay, and this to me is equal addends. So I don't think of this necessarily as trading off. It looks exactly like the algorithm they had before. That's all I'm going to call it, is just equal addends as we're doing it. Okay, and why do I call it equal addends when we're subtracting? And remember, addends are an addition piece, because we're really, like, this problem right here is really saying 39 plus something gets me to 71, which I completely agree with. And what we're doing then is we're just adding one to both sides, keeping that addend equal, if you will. Okay, so the end result here would be the same as asking 40 plus what gets me to 72. And typically that answer is going to be exactly the same. Well, not typically, it always will be exactly the same, but it will typically be easier to compute. So finding this, and again, this could be algebraic. You could think of this as X, you could think of it as question mark, you can think of it as a funky cloud, all of those pieces. Okay. They have an option for drop the zeros. I mean, yes, I guess you could think of this, but really it only happens when all the zeros line up perfectly. If the zeros don't line up perfectly, you don't get to drop them. So I'm not a big advocate of this strategy, especially if you're teaching it to kids for the first time, because if they hear drop the zeros, right, minus 500, they may be like, cool, I'll drop the zeros and then I can subtract. But it's not the same anymore, right? You've completely changed the numbers and the place values have been modified. So while you divided 500 by 10, and really that's what you're doing here, is you're actually saying that if I subtract these numbers and I divide each of them by 100, then my result at the end, I could also think of as being divided by 100. So that would be, for example, 500 plus I don't know what has to equal 8,700. Well, you can divide both sides by 100, right? But you have to divide both sides, all of the terms on a side. This is a distributive property. So that becomes 5 plus, now we'll just call this cloud equals 87. And so the cloud is equal to 82, but the cloud is the box we want divided by 100. So really it's box over 100 equals 82. So the box is 8,200. To me, I don't find a lot of benefit from this one, but yes, it does work if you think of it as dropping zeros to the right, then you're okay. But again, I don't like the language of that, and I think the research is going to show that that's not an ideal technique. Okay. What else do we have here? Oh, there's mental computation. Love it. They said it's not $352, it's $197 off. Well, to me, subtracting 200 be way easier. If I take $200 off, that gives me 352 minus 200. I get 152, and that's what they're showing the students as well. Okay. All right. I'll leave it to you. Again, this is a grade 3 one where they're talking about multiple different strategies for solving. And that gets us into the homework. So boom shakalaka, Bob's your uncle. You are off and running. That takes us out of 3.3. Sorry for the interruptions with the bread, but I'll make sure it doesn't happen in the next one. All right, that's it for now. Off you go.